In this next video, I want to show you how to do the same problem we just did with a pulley with mass and a weight, but using an energy method. If you use an energy method, it actually proceeds much more quickly. So let's go ahead and do this. We'll draw our pulley. Here it is. It has some mass. We'll label that in a second. There is a mass hanging. So there is our diagram. And what do we want to do? Let's label things. So let's say that this is M2 as before. This is M1. What are the things we need? We need a radius. So there's some radius R there. And is there anything else we really need to label here? It's not clear. In our previous example, let me just scroll up here so you can see it. Well, okay, we were given a few other things, but in terms of physical parameters, we had mass 1, mass 2, R, and theta. Let's see if we can do a copy of this. That's really the same question as we have from before. All right, so we'll paste that in here, move it on over, and there we go. So now you guys should be able to see it. Alright, so when we use an energy method, what we're going to do is we're going to say that energy is conserved. There's no friction, there's nothing sapping energy out of the system. So the key ideas here when we deal with conservation of energy is that we have, well, gravitational potential energy, which is basically the mass starts at a certain height and then it's going to fall, and as it falls through a certain height, whatever that height is, so let's say it falls through a height y. As it falls through that height, it loses that gravitational potential energy. That goes into energy of rotation of the disk, and also the falling motion, the translational motion. So really, we can start by writing m1 g y, that's the gravitational potential energy, is equal to, well, the rotational potential energy, rotational kinetic energy, sorry, at the end of it, 1/2 I omega squared, plus the translational energy, 1/2 m1 v squared. So we're looking for that linear velocity v. So again, this is, well, usually we label it like this: gravitational potential energy. This is rotational kinetic energy, and this is translational kinetic energy. All right, so one equation. Well, what sorts of things do we need to do? First of all, we might note that omega is equal to v over r. That v is the tangential velocity, r is the radius of the disk. So we can directly do a substitution in here, and we have eliminated one of our strange variables, omega. You might also remember that we had an expression for y. I'm going to substitute that in just a moment. So we're going to, in basically one step, get to where we did before from a very complicated analysis. So let's go ahead and do this. So we have m1 g y equals, let's see, 1/2. I'll factor that out to start with. I, well, omega squared now looks like v squared over r squared after this substitution here, plus m1 v squared. Let's multiply everything by that r squared term because we don't like fractions until the very end. So we have m1 g y r squared equals 1/2 parentheses I v squared, that r squared comes out of the denominator because I'm multiplying both sides by it, m1 v squared times r squared. Now, if you're observant, you'll note that there's a v squared now in both terms on the right hand side. So let's factor that out. That's really what we're looking for, the linear velocity. m1 g y r squared equals 1/2 v squared times this other chunk, the moment of inertia, plus something that looks like a moment of inertia, m1 r squared. This is getting better and better. It's actually very straightforward algebra. So what we're going to do is we're going to move this over. So we can multiply both sides by 2 and then divide both sides by this. So v squared will now look like m1 g y r squared, and there ought to be a 2 in front of that, and in the denominator we have I plus m1 r squared. So this, as you will see, well, you look at that, you say, that's not quite the same thing. Look at this acceleration. We have this m1 r squared g, and we got all this other stuff there in the denominator. There's a factor of 2, and really this is our y. So let's make our substitution. Our y, because of this idea of angular motion, if that's theta, this of course is not to scale, the arc length s is equal to r theta, as from before, or if we go long enough, we might just say that that is equal to the distance y. The amount of string that is unwound is the amount by which m1 is lowered. So we can then write v is, well, leave it as v squared, we'll do one step at a time, 2 m1 g r theta, and there's already an r squared there, so let's make this an r cubed all over this other stuff. The moment of inertia plus m1 r squared. So if I've done everything right, let's finish it off. V is equal to 2 m1 g r cubed theta, the displacement, over I plus m1 r squared. Now, at this point we're ready to pull out Scratchpad. Let's pop that up. Actually, let's save this one, and then we're going to save a modification of it. Let's save it, and we'll just put it here as a moment of inertia disk 1. And now we're going to save it again. We'll do a save as, and we're going to call it moment of inertia. Moment of inertia disk 2. Alright, now what do we have? All of our givens are the same. We still need to calculate the moment of inertia, but now we're going to get rid of all that stuff. We don't need it. What we need is this formula over here. So it's a little more complicated, but we can work with it. So what we're going to do is we're going to say VF equals math dot square root parentheses. Let's do the numerator. I'll put parentheses around that just to be clear. You don't have to, so I'll do it. It's simpler. 2 times m1 times g times r. R what? R times r. Well, r times r times r. Still probably less typing than using the power function. Times theta. And now let's divide it by, and here I will need parentheses, I plus m1 times r times r. That's my squared. Close parentheses 1, you'll see there's a matching ability. Close parentheses 2, it's matching, so you can see that you've closed your parentheses properly. Now if everything goes well, let's see what we get. Execute, run, no errors, execute, display. Look at that. So that was my previous answer, 11 meters per second right there, and I got exactly the same answer from this. And I hope you can see, okay, here's the work we went through, and most of it was a little bit more algebra. It's sort of, I showed the details of the rearrangement in this case. Here's what came before. Whoa, okay. So there was a whole lot more thinking that had to go on when we use kinematics and kinetics than when we use energetics. So I hope you will consider how to solve problems using energetics when you can get away with it. All right, good luck.